Very much, Christopher. Today I will speak on synthesis of nanopowders in liquid media. We will see some of the most common chemical routes to synthesis in liquid media of nanopowders. And more of these are performed in my laboratory. So we can also discuss about some results about this in my facility. Well, how do we make things small? This is two main approach. The first is the top-down approach. The second is the bottom-up approach. This is a classical vision, classical C of the nanosynthesis. The top-down approaches, for example, are explained in this slide. For example, one common technique is the milling attrition technique. Nanoparticles in this case have a relatively broad size distribution, have varied particle shape or geometry, may contain a significant amount of impurities from the milling media. They may contain also defect resulting from milling. This is a very important point. But they can be readily used in the fabrication of nanocomposite and nanograined bulk materials too. At least in nanocomposite and nanograined bulk materials, the fact that coming from the milling can be annihilated during sintering. Another approach could be the repeated quenching, for example, in which repeated thermal cycling may also break bulk material into small pieces. But the important point is that if materials has small thermal conductivity and large volume, change in function of temperature can take place. This is a very important point for this technique. But with this technique, fine particles can be produced. But the process is also difficult to design and to control to produce particles, the desired particle size and shape. And this is one of the most important constraints of this technique. The bottom-up approach, the matter which we discussed today, in the bottom-up approach, nanoparticles are synthesized, for example, by homogeneous nucleation from liquid and vapor. But they also can be synthesized by heterogeneous nucleation on substrates. They could be heterogeneous substrate nanoparticles core that can grow or other shell of other materials, other oxides of metals, or could be flat or a substrate that permits the growth of new phases, inorganic or metal phases and metal phases. Nanoparticles can also be prepared by phase segregation through annealing at elevated temperature. This is the case, for example, of spinodal, binodal decomposition. It could be used, for example, in glass ceramics approach, in which we have a spinodal decomposition or binodal decomposition in small liquid phases that can be then have a crystallization, and so the form, the shape of this area can drive the shape and the size of the crystallites. Finally, nanoparticles can be synthesized by confining chemical reaction, nucleation and growth processes in small spaces. This is the case of inverse Michelis approach. In the control of the shape at nanoscale, we have to consider the time, duration of heat treatment, the temperature, for example, that can lead to completely different phases, crystalline phases. Zinc blende or wurtzite is an example. We can consider surface energetics. Different phases can have different chemical potential in chemistry. We can use capping organic molecules in order to liquid media for future application. The most common approach is the formation of nanoparticles in a solvent, liquid media. The advantages of these routes is the easiness of stabilization of nanoparticle from agglomeration. We can readily obtain monodispersed nanoparticle dispersion, nanoparticle arrays. It is possible to extract, to make an extraction of nanoparticles from solvent, to change solvents, for example. It's better the approach to manage this suspension, respect nanopowders directly performed from, for example, flame spray and so on. It's possible to perform post-synthesis modification, and it's better to make an application of this liquid suspension on substrates, for example. The control of the process is better, is more than other synthetic routes. It's possible to produce these particles, these materials, in industrial scale. In our facility, we have a reactor able to perform 150 tons per year of nanoparticles. So we can scale up the synthesis to a large scale with this synthetic approach. We can also speak on a sustainable chemical approach, because depending on the solvent, it's possible to speak in this case of, to talk in this case of a green chemistry with respect to other synthetic approach. Well, let me now introduce the first technique, the first route to the synthesis of nanoparticles, the microemulsion synthesis. In particular, I will introduce you the inverse microemulsion technique. In this case, we have a mixture of water, surfactant, and apolar solvent. When we speak about a inverse microemulsion technique, we speak of nano or micro drop of water dispersed in a non-polar apolar solvent. In this case, we can consider this nano drop like nano reactor, in which we can perform the reaction and the production, the nucleation and growth of nanoparticles. And the final size of nanoparticles depend to the size and the form of the water droplet that has been created into the non-apolar solvent dispersion. This is the important point for this technique. In fact, the rate of water surfactant determines the size of micelles, and so the size of final particle. We can also, this rate determines the morphology of micelles. So we can manage as the size, as the morphology of the nanoparticles with the rate water surfactant into the microemulsion dispersion. We can consider this effect as a cage effect, in which the size and even the morphology of the micelles can drive the size and the morphology of final particles. One of the most important surfactants that we use in industrial scale is the sodium bis 2-ethylene-ethyl sulfosuccinate. It's named AOT, and as you can see, we can change the rate between the water pool and the surfactant in order to change the size of the particles. In this case, the radius of the droplet, and so more or less of the final particles, is coming from the volume of water, of the micelles water, and the area of polar group heat. This is the most important critical point to produce water micelles. It's also possible to change the composition of surfactant of polar solvent, in this case isooctane and water, in order to drive the composition of the micelles, and so the composition of the final particles. The shape of the, not composition, the shape of the final particles. As you can see, if we are in this area, this region, spherical inverse micelles are created. Instead, if we are in this region 7, geometrical tetrahedra are created. So it's possible to change the shape of the particles, changing the rate of the surfactant, non-polar, and water system. This is one typical synthesis route for the production of quantum dot, sulfocadmium selenide, cadmium sulfide, sorry. In this case, inverse micelles containing cadmium precursor, in this case cadmium nitrate, AOT, and isooctane, are put together. Inverse micelles containing sulfur compound, in this case diammonium sulfide, water media. When we can mix these two different set of micelles into the reaction reactor, usually we have to give some energy to this coalescence phenomena, for example with microwave or ultrasound application. So the micelles containing the two precursors can collapse together, and the final reaction to obtain the cadmium sulfide can occur. Then, after a centrifugation and washing step, we can dry these micelles. We can eliminate the solvent and partially surfactant, and obtain so the cadmium sulfide nanoparticles with a size and shape that is determined by the size and shape of micelles. Another interesting approach for nanoparticle liquid synthesis in liquid media is undoubtedly the hydrothermal synthesis. In the hydrothermal synthesis, the reactants are dissolved in water or another solvent. In this case, we can speak about solvothermal synthesis in closed vessel. Then this vessel, this bomb, is heated above the boiling point of the materials. Usually, we can use microwave oven to shorten the time of reaction. And we can obtain high purity nanoparticle. It can be also be scaled up to industrial scale. For example, tons of zeolites daily are just now performed. Condition: the solvent can go above boiling point, supercritical. So if we speak about water, we can be in a supercritical region. Usually, we can use basic condition, and this is useful for nano. Many oxides can be produced by this technique. For example, titania, vanadium oxide, spinels, manganese, and so on. We also can produce layered oxides, nanowires, tubes. Carbon nanotubes also can be formed in this way, or some elemental nanostructure, for example, bismuth. The important point is the pH condition when we're speaking about hydrothermal technique. For example, we can note that solubility of water increase with temperature, but in alkaline media, solubility increases dramatically with temperature. Like we can see by this in this slide. You can see the difference between the solubility of silica without and with the addition of sodium hydroxide. So normally the hydrothermal syntheses are performed in basic condition. This is for an example of hydrothermal synthesis of barium titanate nanoparticles, which at 300, 450 degrees are produced very thin and quite regular in shape nanoparticles barium titanate. And two mechanisms are proposed for this synthesis: dissolution recrystallization or in situ crystallization. The best, the dissolution recrystallization is a mechanism proposed by Prinsloo. When wiring at 150 degrees, the water isopropanol ratio, the grain size of barium titanate decreases when the amount of alcohol increases. When so, the solubility of the precursors decreases. Not only, but 10 observation of incompletely reacted powders showed that grains are either amorphous or interiorly crystalline, which means that homogeneous nucleation of growth is occurring instead of heterogeneous crystallization. This is an hypothesis. High resolution TM observation of fully reacted powders reveal the presence of neck between particles. These three experimental observations in the same reaction system provide strong evidence of dissolution precipitation as the primary reaction mechanism. In fact, another proposed mechanism is in situ crystallization, in which non-dissolved titanium oxide reacts with barium and hydroxide ions. This was proposed by Eckert in 1996. This is another synthesis performed in spherical laboratory of zirconia nanoparticles, which a precursor, for example, zirconium chloride is added to sodium hydroxide. Then we have a first stage in which we have a coprecipitation of the zirconia hydroxide, and then we perform a hydrothermal microwave assisted stage at pH 9, temperature 195 degree, time 5 hours, and power for 6 vessels 540 watt. After this hydrothermal synthesis at stage, we can filtrate, dry, and grind the powder, and this is the how they appear to a TAM image. Interesting to note that we have a mixture of monoclinic and tetragonal zirconia with diameter of 27 nanometer for tetragonal and 9 nanometer for monoclinic zirconia. This is a simple and common apparatus for hydrothermal synthesis under microwave condition. We have a Teflon vessel arrays, a Teflon with thermocouple, or pressure probe in order to control the condition of hydrothermal microwave-assisted synthesis. Then we speak about the polyol synthesis. This is very interesting synthesis. The polyol process consists in a rapid nucleation followed by slow particle growth at high temperature. Generally, we use a complexing solvent with a high boiling point in which this nucleation step occurs. And then we have to control only the growth mechanism of particles. It's not so simple, but the growth step of particles is controlled by the complexing behavior of the solvent. This is a key point for polyol synthesis approach. We can have two schemes. Scheme A, a rapid addition of precursors at high temperature in the vessel containing a complexing solvent with a high boiling point. Normally, we use polyethylene glycols, and we perform this reaction at more than 180 degrees. It's very, very high temperature. The diethylene glycols have a complexing behavior against the precursors and then the nanoparticles that are growing. The scheme B, we can mix precursors at room temperature, and then a fast heating step can follow. This is the two approach to polyol synthesis. This synthesis permits to control the stoichiometry. It's very flexible. We can make many different particles. We can dope particles. We can dope metals. We can dope oxides with other metals. We can control the size dimensions. We can control the size distribution. Normally, we obtain monodispersed nano suspension. And we can avoid settling phenomena, precipitation phenomena. This is very important in industrial scale approach. Then this led to an easiness of application. Homogeneous nucleation occurs via a stepwise sequence of bimolecular addition until a nucleus of critical size is obtained. This is the classical approach proposed by Lemaire. And highly monodispersed nanoparticles, as I speak before, are formed in the processes of nucleation and growth. If the process of nucleation and growth can be successfully separated. This is a very important point. The nucleation process must be fast, but growth process must be slow. This is the key point for polyol approach to nanoparticles synthesis. This is a typical synthesis of titanium dioxide. We start from titanium precursor, for example, an alkylate, titanium alkylate. Then with adding complexing solvent, polyethylene glycols, diethylene glycols, acetic acid as a stabilizer, and water in a rate, pre-precise rate. We can heat this mix, and after distillation step, we can obtain a colloidal suspension. can see the colloidal suspension on the top of the slide. The size distribution in volume and number performed by dynamic light scattering show a size of about 7–10 nanometers of titanium nanoparticles with the diffraction, high resolution diffraction measure. We are able to confirm the mineralogical phase of these particles is anatase, and this is very important for the photochemical behavior of these particles. Especially, they can be used in the preparation of photoactive surface, for example, for the depollution or antibacterial surfaces. And also the TEM image confirm the size of these particles. These are some of the spherical nanoparticle produced with this technique in spherical. We have many different particles, metals, like for example gold, radium, platinum, binary metals, because it's very interesting to this technique because it permits to dope particles, metals with other metals, oxide with other metals, and so on. Nano coatings, for example, we obtained silver shell on titanium dioxide core, or silica zirconia particles, and so. Otherwise, we can obtain oxides, like for example, titanium oxide, iron oxide, zirconia oxide, as you can just see, alumina oxide, and also oxide more complexes, like for example, spinel-based oxides, like for example, ferrites, or titanite, and so on. We have also obtained hydroxyapatite with this polyol synthesis method, with very interesting properties. As you can see, we can also perform post-synthesis routes very easily by this polyol approach. On the right of the slide, we can see a silica zirconia double particles performed by a double step of polyol synthesis. In the second, in this image, you can see a super paramagnetic nanobiocarrier that is made by an inorganic core made by a cobalt ferrite surrounded by a proteinaceous shell. All is linked by these organic molecules that permit the link of the bovine serum albumin to the inorganic core shell. This product, this material, is very interesting for in the cancer treatment because if it is immersed in an electromagnetic field, and it can be heated, and so we can perform heating of at a cellular level of tumoral cell. The so-called high temperature heating treatment of cancer cells mediated by electromagnetic field. It's possible also to change the lipophil hydrophil behavior of these particles, changing the functional ends of these molecules. This is very interesting. We also can have another post-synthesis treatment for powder obtainment. This is a scheme for starting from nanoparticle sol to arrive to powders. There are mainly two routes. The first is to precipitate the nanoparticles, to filtrate them, to obtain wet powder with repeated washing treatments, then drying it. The problem is, yes, we obtain dry powder, but hard aggregates are obtained. It's not so good for industrial and for us. So the best way is to obtain a soft aggregate by a spray dry approach. As you can see in this picture, we can obtain this aggregate of about 10-20 microns in size that can be easily dispersed in liquid media. Another interesting approach is the precipitation, co-precipitation. Here we have some easily recipes of to obtain silica nanoparticles. In this case, we can mix a precursor, silica precursors, tetra ethyl orthosilicate, and with addition of a base, for in this case ammonium hydroxide, drop by drop. Then we obtain, after addition, sonication, we obtain silica hydroxide, and then we can dry it to get fine particles of silicon oxide. This is the picture of this preparation. Also, this precipitation, co-precipitation route can be used to synthesize zinc oxide nanoparticles. The interesting is to note how different routes of synthesis, synthetic routes, can lead to different shape, to different morphology of particles. In this case, we use zinc precursors, an acetate, with added to a base, a triethanol amine, and water. After under this triethanol amine is added dropwise under nitrogen atmosphere, then it was sonicated for 2 hours and 80 degrees, and the resulting light yellow color precipitate was washed several times and then dried. And this is the results, the nanorods of nanorods, not so nano, but the rods of zinc oxide. Instead, if zinc acetate was added to potassium hydroxide prepared in methanol and washed, we obtain rounded nanoparticles after a drying stage at 130 degrees. The particle size is thinner than the first case and is about 80, 120 nanometers. Finally, let me to introduce a interesting synthetic route named Sonochemical nanosynthesis. In the sonochemistry, molecules undergo to a chemical reaction due to the application of powerful ultrasound, normally in the range of 20 kilohertz, 10 megahertz. In this case, acoustic cavitation can break chemical bonds. And we can speak about a hotspot theory, as bubble implodes very high temperature, until 5,000, 25,000 Kelvin are realized for a few nanoseconds. This is followed by very rapid cooling. We can speak of 10 power 11 Kelvin for over a second. So high cooling rate hinders product crystallization. Hence amorphous nanoparticles are obtained. Solvent or solute molecules present within the bubbles are decomposed under this extreme condition and generate highly reactive radicals. And this is a very interesting point because it can be applied to all the nanoparticle synthesis that concern metal, like silver, for example, as we can see in the next slide. Is a process very useful for preparation of amorphous products. We speak about cold quenching. Is it very interesting for the insertion of nanomaterials into mesoporous materials by acoustic streaming. Deposition of nanomaterials on ceramic and polymeric surfaces is a very interesting technique. This is also very interesting technique for the formation of proteinaceous micro and nanospheres. It is used also in pharmaceutical field to obtain nano cage in which delivered the pharmacological species. And we can obtain also very small particles. This is a mechanism which, for example, during a sonication stage, we obtain free radicals can react with metal precursors in order to obtain metal nanoparticles. And for this route, with this route, we can obtain, for example, silver nanoparticles by this reaction route. Also, it's possible to prepare gold nanoparticles dispersing gold precursors, like, for example, gold tetrachloride in a solvent, in alcohol, in order to obtain gold nanoparticles, metal gold nanoparticles, then side products and side products. It's very interesting approach. We can make many different examples. We can obtain for example, gold, cobalt, metal, iron. It's not very simple to obtain iron metal nanoparticles in other synthetic routes. In this case, is very interesting and very simple. It's not so difficult. We can obtain nanophased oxides, titania, silica, zinc oxide, and zirconia oxide, and so on. We can obtain also magnetic nanoparticles. Very interesting, as I told you, in hyperthermal treatment of cancer at cell scale. Also nanowires of selenium has been obtained. We can also speak about sonoprocessing of nanocompositors. Power ultrasound can assist in synthesis, blending, dispersion, erosion testing of nanocomposites. High-intensity ultrasound used with melt processing for polymer and clay nanocomposite also can be used. For example, polypropylene, polyester clay, and polymethylmethacrylate clay nanocomposite can be prepared by ultrasonic assisted melt mixing. It's very interesting for industrial field, especially in polymer industry. And we can obtain superior overall homogeneity of composite and improved performance by this way. This is you have the mechanism of sonofragmentation. In which we have a bubble. The bubble collapses due to implosion. A particle fragments are produced due to violent bubble collapse and interparticle attrition. These are the two mechanisms that are proposed for this. This is a typical experiment in which the sample is sonoprocessed, in which we have micron-sized feed particles in distilled water, and after probe sonication, we obtain micro-sized particles seated at the bottom of the tank of the reactor, and submicron and nano-sized particle on the top. We also can perform blending between particles for composite formulation, in which case a submicron, micron-sized blend can be obtained by a sono process stage. Also are able to be, we can prepare a polymer precursors, mixing microparticle with nanoparticle or with other precursors, and then adding a solvent suitable to be used for the polymer we want to use, and then we can obtain particles dispersed in a solvent suitable to be used in the polymerization, for example, stage. Okay, so I can I wanted to show you the facility of Spherical Research Center. We are located in Tuscany, at Vinci, the heart of Tuscany, the town of Leonardo, and this is the laboratory, and this is the Colorobbia plant, and these are my collaborators and the staff, and some of the activity of my research center for nanosynthesis, analysis, and glass ceramics synthesis, glass ceramics preparation. So, thank you very much for your attention.